All right. Well, hello, everyone. Good morning, good afternoon, good evening, whenever you're watching this. This week on the soils recitation, we are going to go over some more settlement problems, some consolidation, compression curve indexes, and things of that nature. If you guys have any comments, concerns, please let me know, and we can address them as soon as possible. Just like one bite from Barstool, this will be a one take, no edits kind of deal. And here we go. So this first problem we have today, we are going to plot the following data and determine the pre-consolidation pressure and the modified compression index for this consolidation test given. So this percent consolidation is essentially just strain. And we're given all these things down here, but all we really need is the strain and the pressure for this problem. So when we graph all of this, we get this nice little looking graph. But what the problem is asking for is that we find the modified compression index. And we are going to do that. Make sure I get my pen here. That C sub C strain, which is our compression index, equals, so we're essentially just interpolating from a line. And I'll show you here in a second what line we're going to interpolate from. Over. And since we're pulling this from a semi-log graph, we have to include the log for the x-axis. All right. So moving on. So here's our curve, and we're going to find that our compression index is going to be essentially this curve right here, because this is where we recompress the clay. So think about it for those who haven't done a consolidation test or ever seen one before. We load the clay for a certain amount of time, and then we keep increasing the load, recording the strain until a certain point. And then we're going to let the clay rebound. And then as it comes to the amount that will rebound, or the amount that the clay will swell, essentially, because you think about it, we compress it and then it's going to try and go back to its original shape, but it can't truly go back to that because we've compressed it so much. So once it gets back to as much as we think we can let it rebound, we're going to compress it again and then over compress it, because clay understands how much stress has ever been applied to it. So essentially here is that we are stretching it past its knowledge. And then here is where we're going to get closer to the end of the test as we unload the clay. So this comes into question of, how are we going to find these points from this graph? Well, like I said, we're going to use this essential compression curve, which if we're ignoring this and this, that's where we're going to make our line. And our line, if I can draw it straight, will be just along like that. So something like that. This is a line that we're going to pull values from now. And when I'm pulling values, I'm going to say, well, I'm also going to extend a little bit, because then I'll make things a little bit easier. So we're going to say, well, down here, we're going to pull from the 25%, and then we're going to pull from up here, so around 3%. So using those two values, and we're essentially going to interpolate, we're going to say, all right, 0.25, computing the strain back from percentage back into a decimal, minus 0.031. We have the log of 8,000 divided by 300. So when you do that math, actually we'll just scroll down, and when you do that math, you will get C sub C strain equals 0.154. So simple enough. So that's half the problem. So now we need to determine the pre-consolidation pressure from this graph. So how are we going to do that? Well, I'm going to write down here. If you guys look at figure 8.6, then this will show you a good way to pull a minimum, a maximum, and most probable pre-consolidation pressure. So we're going to say, all right, the minimum is probably going to be somewhere here. So this is, actually, I'm going to do that in a different color. Let's say green. So our minimum is probably going to be somewhere here. And our maximum is probably going to be somewhere right here. So we need to go somewhere kind of in the middle. And I think for this problem, our middle is going to be somewhere right here. And we're just going to, if I can draw it straight. So this is where our middle is going to be. So from there, I'm just going to go up on the graph, straight as I can. And we should get approximately sigma prime P equals 260 kPa. And that's it for this problem. So I'm going to box those real quick. And that's all we need for this problem. Next, we're going to do something a little bit more similar as to what we did last recitation. And so here's our problem. This figure here shows that the soil profile of the site where you plan to lower the water table. Why is lowering the water table important? Because it's going to affect the effective stress being applied onto whatever we're trying to assess. So it's like, will the clay have more pore water pressure here or less pore water pressure? Why is that important? And we'll find out. You have results from 2 consolidation tests, which is great because sometimes you won't have any consolidation tests be performed because they're expensive. One from the upper 12-foot thick consolidation crusts and one from the lower 32 thick normally consolidation zone. Plan to lower the water table from its current 12 feet to 20 feet below ground surface. The consolidation properties for each layer are shown. So assume full capillarity. And then we have A, compute the effective stress in the middle of each layer before and after the water table is lowered. And then B, determine the total settlement that will result from lowering the water table. So to do this, we're going to compute the vertical effective stress in the middle of each layer before and after the water table is lowered. So we're going to do before first. I'm going to lower this so we can just see the calcs now. So we're going to say layer 1. We're going to have our total stress equal the 6 feet times 120 PCF, which was given to us, which is going to give us 720 PSF. And since this is above the water table at this moment, the pore water pressure is just going to be 0. So therefore, the effective stress is going to be equal to the total stress for the first layer before we lower it. So this is layer 1. So now for layer 2, we're going to do, all right, total stress equals 12 feet times 120 PCF. plus the 16 times 118 PCF. So therefore, we're going to get a total stress equal to 3328 PSF. Great. So now we're underneath the water table. So let's calculate that pore water pressure. So we got 16 times the unit weight of water, 62.4, which will give us 998.4 PSF. So now we're just going to use what we have and calculate for our effective stress, which we all know that the effective stress will just be the total stress minus the pore water pressure. So to get this, we get effective equals 328 minus 998.4. So therefore, the effective is going to equal, I'm going to write this down below. I don't like how it's edging the paper. It's going to equal 2329.6 PSF. So this is all before the water table. And I'm going to underline everything that's important so far for us for each layer. So that way we can keep this in mind, so when we lower the water table, we can see what the change is. So now, after. So for layer 1, there's really no change because we're lowering it. So what's dry, it was dry. So for layer 1, there is no change. So sigma prime V naught equals 720 PSF. So everything is virtually the same. But layer 2 is going to have some drastic changes to it. So let's start with determining the total stress. So we got 12 feet times 120 plus 16 times 118, which equals 3328. Nothing too unusual there, but the pore pressure is going to change. So we got 8 feet times 62.4, which equals 499.2 PSF. So now let's calculate the effective stress, which is just going to be subtracting the total minus pore water. And when we do that, so 328 minus 499.2 equals 28.8 PSF. So I'm going to underline that one real quick, and let's just look back at what we had. So for the before, we had 2329, so 2828. So now the effective stress is increasing. So we have everything that we need for part A of this problem. So now for part B. So we need to determine total settlement that will result from lowering the water table. So this settlement is all going to be in layer 2. So we're going to do that by saying, all right, the change in effective stress, which is 28.8 minus the 2329.6. So when we find this change, we go, okay, we got a change of 499.2 PSF from before and after we lower the water table. And for layer 2, we're going to assume it's normally consolidated. Therefore, sigma prime P over sigma naught or sigma V naught equals 1. And then also, since that's true, I'm going to write this below. Sigma prime P equals sigma V naught. So therefore, our pre-consolidation pressure is going to be 2329.6 PSF. So now we're going to use equation 8.13, and we're going to see this total settlement, C sub C strain, times H naught, so the height of our soil layer, V naught plus delta V over sigma V naught. So we have this, and we know that this is going to be the 32 feet because that's what we need to assess. We were given this value from the figure up here. So I'm going to scroll back up a little bit. So we were given this, change it to red. So we were given this value. And then from everything else that we've determined so far, we know these pressures and that change in pressure. So now I'm just going to plug and chug, and I'm going to do this in blue just to change things up. So we got 0.185 times 32 of the log of, one more time, 3329.6 plus 449.2 divided by 23. Oh, sorry. This is supposed to be, erase this real quick. It's supposed to be 23. So we got 2329.6. So when we do this math, we find that our total settlement occurred 0.499 feet, but we want this reported in inches because this is a much more realistic settlement report. So we'll say, instead of giving this obscure half a foot, we'll say it's 6 inches of settlement. And that will be our answer. So nothing too much to it, just a lot of going through and making sure that we filled everything out. So yeah, I'm just making sure that we're, they're going to try and give you more than what you need. But since we know this is where most of the water is always going to be, this is really all that we need to assess for settlement. So hopefully that helps you guys. If you guys have any questions, please let me know. And this is going to be, so there's more to this recitation, but the rest of this recitation is going to be in other videos, which is going to go over software that calculates this for us. And the software is really nice and it can do a lot of things, but you need to know the basics like this to understand what it's telling you. So I'm going to stop this video and I will see you guys next time.